Okay, welcome to the Graphs and Matroids seminar. Our speaker today is James Davies. He's going to tell us about odd distances in colourings of the plane. James, take it away.
Thanks for the introduction and invite to talk in the seminar. And feel free to stop me for questions at any point. So I can't talk about any problem in Euclidean Ramsey theory without first talking about the Hedrickson-Nelson problem. And this is this famous problem of how many colors you need to color the plane so that you have no two monochromatic points at unit distance apart. So from the start, it was known that you have this upper bound of 7 for the Hedrickson-Nelson problem, and you can get this from things like this hexagonal tiling using 7 colors. For a long time, the best known lower bound was only 4, and this can be realized by some very small 4 chromatic unit distance graphs. And then a few years ago now, there's this big breakthrough of a construction of a 5 chromatic unit distance graph, which was shown by this monster of the graph, which requires a computer to check that you can't color with 4 colors. So, answer to Hedrickson-Nelson problems between 5 and 7. Going down a dimension for a bit, I want to talk about this very nice theorem on coloring the integers. And this is one of the first applications of the ergodic method. So this says if you have some polynomial with integer coefficients, and so f of 0 is 0, so constant term 0, then in any finite coloring of the integers, you can find a monochromatic pair of distinct integers so that their difference is equal to some value of this polynomial. So one nice example of this is if you just take nth powers, so f of x equals x to the n. And then we can construct a graph from this. Our vertices will be the integers, and we have an edge for any pair of integers a, b, so that their difference, a minus b, is equal to one of these x to the n perfect powers. And this theorem says that this has unbounded chromatic number. And actually, this is a fun example of a triangle-free construction of graphs with large chromatic number. Because if you take n at least 3, then by Fermat's last theorem, this graph contains no triangle. There's one way to get graphs that are triangle-free and have large chromatic number. Now, this is a very nice theorem, but there's one kind of strange-looking condition in it, which is this f of 0 equals 0, or constant term 0 requirement. And it's clear that something like this must be necessary, because if you take something very simple, like f of x equal to 2x plus 1, then now this theorem fails. When you've got f of x equal to 2x plus 1, now you've got edges for odd distances, or odd differences, and then you can get a 2 coloring by coloring all even integers blue and all the odd integers red. So you need some kind of requirement like this. But we can ask what happens if we go back up a dimension again. So what happens if we go up into the plane now with our f of x equals 2x plus 1? And this is exactly what Rosenfeld's odd distance problem is. He asks for the chromatic number of the odd distance graph, where now our odd distance graph is the graph whose vertex sets the points of the plane, and we have an edge whenever their distance is odd integer. So the first thing with this problem is we can see that nothing super crazy goes on. We can at least get a countable coloring. And we can do it by taking any infinite tiling of the plane, avoiding unit distances, like with this hexagonal tiling, but now we just give every single hexagon, every tile, its own individual color. And this gives you a countable coloring. But then the bigger question is whether or not this would be infinite. So one easy way you can hope to try and get a lower bound for chromatic number of a graph is to look at cliques in the graph. There's a set of pairwise adjacent vertices. In cliques, each vertex needs its own color, so this would be an easy way to lower bound chromatic number. But this strategy doesn't work for your distance graph because already we don't have a 4 clique. It's not an odd distance graph. So you can't do anything as simple as that. Now, any unit distance graph is an odd distance graph. So we have the same lower bound as we get from unit distance graphs. So this monster 5-chromatic unit distance graph gives us a lower bound of 5. But actually before this, a much smaller, simpler 5-chromatic odd distance graph was known. And then just a couple of years ago, this was improved, and there's a construction of a 6-chromatic odd distance graph. And that was shown by the second monster of a graph. And this is again another one of these constructions where you need to check by computer that there's no 5 coloring of this thing. One other result that was known for Rosenfeld's odd distance problem is actually, if instead of asking for a chromatic number, you ask for the measurable chromatic number. For measurable chromatic number, now you want all your color classes to be measurable subsets of the plane. Then actually it was known for a while that the measurable chromatic number is unbounded. And this uses some spectral method. And the theorem I want to talk about today is that for the chromatic number in general, the odd distance graph has infinite chromatic number. So we improve this lower bound of 6 to some infinite thing, and we get rid of this measurable condition. Okay. So odd distance graph is quite a complicated thing. It's uncountable graph on vertex set being the plane. So we can start off by just playing around with something simpler. And the natural first subgraph to consider could be on the integer lattice. So just got the points of the integer lattice, and we have an edge for when the Euclidean distance is odd. So here we've of course got the edges making up our infinite grid. These are all unit distances. But also horizontally we've got infinite complete bipartite graphs, and vertically as well. We also have some extra kind of edges. For instance, we can have edges of this form that go 4 along and 3 up. And this is just Pythagoras, 4 squared plus 3 squared is 5 squared. So this is an odd distance. So perhaps already you have that odd distance graph on the integer lattice has infinite chromatic number you could hope for. But this turns out to be false, and actually you can 2-color it. So the reason you can 2-color it is that whenever we have an edge like this, here we're going 4 along and 3 up, always exactly one of the 2 coordinate differences is odd and the other is even. So if we just color our integer lattice according to the sum of the coordinates mod 2, then we get a 2-coloring. So unfortunately, this doesn't work just looking at the integer lattice, but now we could try again and see what happens with another lattice. So maybe the next most natural lattice to consider is a triangle lattice. And this already looks a bit better because now we have some triangles in here. So chromatic number is going to be at least 3. And as before, we've got these infinite bicliques along these lines of the lattice. And we can also get some edges of another form. So for instance, you can calculate that going 5 along and 3 up in the lattice gives you an odd distance. And this again also looks a little better than before because we have a bit more diversity in terms of the powers of 2 dividing these coordinates. Now these are both odd. But we still run into a similar problem that whenever we have one of these edges, at least one of the coordinates must differ by some odd number. So if we color according to each coordinate mod 2, we get a coloring of 2 times 2 colors. We get a 4 coloring. So again, odd distance graph on this triangle lattice is finite chromatic number. We could 4 color it. So this again doesn't work, but it's also kind of encouraging, right? Because we've done better than before the integer lattice. We've managed to get so that this other lattice starts a higher chromatic number. So what we can aim to do is just to keep choosing better and better lattices that give us higher and higher chromatic number. And this is exactly what we end up doing. So the lattice we're going to take is going to be generated from 2 unit distance points. One will just be the standard basis vector 1, 0. And then we'll take this second strange looking EK as our second part of the basis. And then what we'll aim to prove is that the odd distance graph on this lattice is always going to have chromatic number at least k plus 2. So we can take k big and get as big chromatic number as we want. Okay, so this is the plan. We're going to look at chromatic number, the odd distance graph on these 2-dimensional lattices. So it'd be convenient to have some better notion for what these graphs are. Actually, they're just going to end up being Cayley graphs over our group Z squared. So a Cayley graph over our Z squared, this is going to be going to have a vertex set being Z squared, and the edges are going to be given by some set of generators. These are going to be non-zero points in Z squared, which will be centrally symmetric. So if we have something as a generator, we always have its negative as well. And then our edges is just going to be the points in Z squared, these differences inside our generating set. So as an example, if we've got this set of generators, see, these correspond to these edges around 0, and then we're just pasting this in transitively everywhere. So the set of generators give us this Cayley graph over Z squared. Okay. So we can straight away, when we're looking at the odd distance graph on one of these 2-dimensional lattices, turn this into a Cayley graph over Z squared. We're being generated by these 2 basis vectors. These will just be our generators of Z squared. And then whenever we have a difference that gives an odd distance, this can just be in our generating set, like so. And now we can observe one nice property that we have of a generating set in such a Cayley graph, which is if we ever know that one element is in our generating set, then we also know that any odd multiple is also in a generating set. And this is just because we've got an odd distance witnessed by this, timesing it by an odd times odd is an odd number, so we've got another odd distance. So we know that our generating set can be closed by taking odd multiples. So I want to not worry too much about being an odd distance graph so much for a bit, and instead try and think about how I can construct a Cayley graph with this kind of property of large chromatic number. So I want to take for granted that I can always add odd multiples to my generating set. So my generating set will be made of some primitive set of generators dk, and then the odd multiples. That's something I can take for granted. And I want to construct something like this without cheating too much with large chromatic number. And what I mean by cheating too much is we need to go back around eventually and hope to be an odd distance graph. So I can't just add in generators to create a big clique because I know that's never going to be an odd distance graph. So I don't want to cheat too much there, and I'll hope it works out later. Okay. So that's our strategy for the kind of graph we want to build. But we need a way to examine the chromatic number of such a thing. And for this, we use this strange looking ratio bound theorem. So what this says is if we've got our Cayley graph over Z squared with our generator C, and we've got some weights in our generators, which will again be centrally symmetric, we give some generator the same weight as negative. Then what we look at is the sum of their weights, R, and we're going to look at the minimum of this strange looking W hat function. And we get a lower bound for the chromatic number of 1 plus the sum of these weights divided by the negative of the minimum of the strange W hat function. And what this W hat function is going to be this exponential sum, where for U in R squared, we've got the summation of exponentials, where for each generator x, we're timesing by the weight of that generator and timesing it by e to the 2 pi I times the inner product of our u and our x. So this is a strange looking thing, but if you're familiar with Hoffman's ratio bound theorem, then essentially it's just coming from a weighted version of that. Take some limit to infinity of that, and this is what you get. So roughly speaking, in Hoffman's ratio bound theorem, you're looking at this k-regular graph. That's what the sum of weights corresponds to, being k-regular. And you're looking at you get a bound from the minimum eigenvalue. This is what this minimum here corresponds to. Our strange w hat function more or less corresponds to the eigenvalues of this graph. And because this is an infinite thing, things are smoothed out. So we've got this infinite rather than finite eigenvalues. Okay. So the point is, for this theorem to be effective, we need the sum of weights to be much larger than the infinite of this exponential sum. So this will be our aim. We want our Cayley graph with generator C and some weight function. So that the sum of weights is going to be much larger than the negative of this infinite. Okay. And then again, going back a little bit, we want our Cayley graph to be of a form we've got some primitive set of generators and odd multiples. And it'll be convenient just to take the odd multiples up to n. And if we're just taking these first n odd multiples, this allows us to split up the summation in our strange w hat function nicely. All our generators are of the form of some primitive element in D times an odd multiple. So we just split the summation up into two, where we've got our primitive generators and then these odd multiples, like so. So I've got the weight of this odd multiple of primitive generator x. In this experiment, I've got this, again, odd factor of 2j minus 1. So we're splitting this exponential sum up. Some natural weight function to begin with and to write out would be just some averaging out function. So 1 over n. And because all we really care about is kind of the average negative contribution you can get out of these things. So just averaging is natural. And now let's keep things a bit simpler for a bit and not worry about this u in the product x that we can get for all our values of u and generate as x. And we'll just see what happens if we fix this as some alpha and look at how this exponential sum is now going to behave. So we want to look at how this exponential sum of 1 over n, something between 1 and n, of this e to 2 pi I times 2j minus 1 alpha. If we learn more about this, then we'll learn how to handle something like this. Okay, and again, we only care about what alpha is mod 1, if this is periodic function. Okay, so a first case we can consider actually ends up being quite encouraging. So if two alphas roughly equal to 0 mod 1, or in other words, alpha is bounded away from 0.5 mod 1, then actually, as n gets big, this sum tends to 0, which is exactly what we want to get an effective bound Hoffman's ratio bound theorem. So one way you can show this is just observe that this is some geometric series. This is being times by e to 2 pi times 2 alpha each time. You can manipulate that and you end up getting 0. But you can also look geometrically and see that this is exactly what you'd expect. So we can look at our first part, e to 2 pi I alpha, on a complex circle. And this is going to be bounded away from 1 and minus 1, because our alpha is bounded away from 0.5 mod 1. And then the next term, this e to the 2 pi I times 3 alpha, this is going to be moving around the circle, because our 2 alpha is bounded away from 0 mod 1. And then we can keep going 5 alpha, 7 alpha, and so on. And what's going to happen is we're going to start doing laps of the circle. And we kind of have this ergodic behavior where we're going around the circle many times evenly spread out. And then you're going to expect that if you take the summation and average it out, on average, this is going to tend to 0. Okay. So this is encouraging because it shows that in almost all cases, we get exactly what we want, and that this exponential sum ends up being small. But we still need to consider these 2 other cases, which is when our alpha's about 0 or about a half mod 1. So let's look next at when it's about a half mod 1. And here it's convenient to pair some of our terms in the exponential sum. So because we've always taken, in our generating set, if we have something as a generator, we always have this negative. So we compare these exponentials and we end up getting some cost function here. But now with this weight function, we can run into a problem. So although we know that alpha can be very close to 0, this doesn't necessarily tell us or give us any bound on what 2n alpha can be. So for instance, 2n alpha could be about 3/4. And then as we're looking at the summation on the circle, we're going around very slowly, around 3/4 of the circle. And then this ends up being bad because, roughly speaking, we've got half the circle where we're getting this negative contribution, and only a quarter where we're getting this positive contribution. So here we're getting more negative contribution, and our summation can be bounded below 0, which this will then be a limiting factor of a ratio bound if this is happening. So this is something we need to avoid. And to do this, we can just pick a slightly more complicated weight function than our averaging 1/n. So what we end up picking is this kind of weight function. We're assigning a different weight for each of our odd multiples. So for our jth odd multiple, we're adding on this factor of m+1 minus j divided by m+1. So for our first, this times 1, our first odd multiple, roughly speaking, we're going to have full weight. And as we get closer to our nth odd multiple, we're linearly decreasing the weight we give this generator. So looking at this picture, at least in this case, this ends up being good, because although we're only getting positive contribution from quarter of the circle, this is going to have higher weight if this is for smaller odd multiples. So we end up getting, we get extra positive contribution out of this. And it turns out that this works out with this weight function. So again, because our 2 alpha gets very small, we can approximate the summation by some integral. You remember integration from school, and it magically works out. So with this weight function, we get everything gets big. For alpha near 0, this summation is always at least 0, so we're happy here. So we should be a little careful because we did change our weight function. So our previous case will be a little different, but things work out the same way. You still have this kind of ergodic behavior, and it will tend to go still. Okay. So at this point, it looks very encouraging because we've shown that all but possibly one case is a good case for us. But now we need to consider this last case, and then things look less positive. And this is the case where alpha is about a half mod 1. So let's just say, see what happens if alpha is exactly a half mod 1. Well, now in each of these experiments, we've got this odd multiple of a half. So mod 1 is still a half. And then this is going to be equal to -1 for each term in the summation. And then this is kind of a disaster because now we're taking the negative of the sum of weights. So we're getting full negative contribution in this case. And this is completely useless for getting anything out of the ratio bound theorem. So this is a problematic case. On the other hand, we haven't actually used much about our generators yet. All we've really been looking at is that we have these odd multiples of our primitive generators. We haven't said anything about what our primitive generators are. So the idea now will be that we want to choose our primitive generators to avoid falling into this bad case too much. So this bad case was happening when our alpha was equal to about a half mod 1. And what our alpha was before was this inner product of u and x, where u was the sum element in R squared, and x was in a primitive generating set. So if we can choose a large primitive generating set so that we can only ever fall into this bad case where this alpha, u in the product x, is about a half mod 1, that bad case only happens a few times, then we'll be able to get a good bound on this good bound on this exponential function, be able to get a good bound out of a ratio bound theorem. So that'll be the plan. And to do this, it really revolves around just quite simple lemma and being able to apply this effectively. So what this says is if we have some increasing integers, t1, t2, t3, between 0 and 2k, then we can find non-zero integers, c1, c2, c3, with c1 and c3 even and c2 odd, so that this summation of points in z squared is equal to 0. So for this summation, we're taking for each I, summation of ci times this point in z squared, which is 2 to the power of 2k minus ti, and then in the second coordinate 2 to the ti. So why is this true? Well, first of all, we can take some c1, c2, c3 that are non-zero, so that this sums to 0. And this is basically just because z cubed is not a subgroup of z squared. So some non-zero ones exist. And if we multiply out by a factor, we can assume that their greatest common divisor is 1 as well. So now we can show that c1's even now. And to do this, we just want to look at the second coordinate of the summation. Again, this needs to sum to 0. But these powers of 2 in the second coordinate is 2 to the t1, 2 to the t2, 2 to the t3. These powers of 2 are increasing because our t1, t2, t3 are increasing. So if we look at this modulo 2 to the t1 plus 1, then for this to be 0, c1's got to be even, because each of these terms is going to be 0 mod that. So looking at these increasing powers of 2 in the second coordinate, we see that c1's got to be even. And now we can do exactly the same trick in the first coordinate to show that c3's got to be even. Now our powers of 2 are decreasing in the second coordinate, so the c3 has to be even for the summation to be 0. And then because c1 and c3 are even, greatest common divisor is 1, c2's got to be odd. Okay, but why is this useful? Well, it actually gives us a good primitive set of generators that we can pick. And our primitive set of generators is going to be exactly coordinates in z squared of this form, where in the first coordinate we've got this decreasing power 2, and in the second we've got this increasing powers of 2. And why is this good? Well, if we have some u in our R squared, then we can show that there's only at most 2 integers t between 0 and 2k. So that the inner product of our u and our coordinate 2 to the power 2k minus t, 2 to the t, is about a half mod 1. And again, this half mod 1 is what a bad case is. So this will show that a bad case would only happen twice, at most twice. So why is this key lemma true? Well, we suppose it isn't true. And then that means that there exists 3 of these integers, t1, t2, t3, and suppose they're increasing. And so that each of these inner products is about a half mod 1. And then we're going to just apply this previous lemma to get these c1, c2, c3, so this sums to 0. And take this inner product with our u again, this alpha beta. And because this is 0, we know this inner product should be 0. But now we can get a contradiction because we know individually each of these is a half. So this should still be equal to about the sum of our C1, C2, C3 divided by 2. And because C1 and C3 are even and C2 is odd, this is an odd number divided by 2. So this should be equal to about a half mod 1, but we know this would be 0. So we get a contradiction here. Okay, so this shows us that this set of primitive generators is a good choice. We're only going to fall into this bad case at most twice. And again, the set of primitive generators is these points in z squared of a form 2 to the 2k minus t, 2 to the t. And really the key property here is this sandwiching property of, in the first corner, with decreasing power of 2, in the second we're increasing. Okay, so now we can tie everything together. This is going to be our primitive set, and then we're looking at odd multiples of this. Let's say the first n odd multiples. We're giving it this weight. We've got this averaging 1 over n factor. And then for our jth odd multiple, we've got this linearly decreasing factor of this n plus 1 minus j over n plus 1. Our sum of weights, just from our choice of weights, ends up being equal to the size of our primitive generating set dk, which is equal to 2k plus 1. And then combining our examination of this exponential function, we only fall into this bad case at most twice, which is giving us at most this minus 2. So it then gets big, the minimum of this function ends up being at least minus 2. And then we can apply our ratio bound theorem. So the chromatic number of this Cayley graph, taking this limit as n gets big here, is going to be at least this. Our summation here is our 2k plus 1, and over the minimum of this function, which is going to be at least minus 2 as n gets big. So then we get that the chromatic number is more than k plus 1, so at least k plus 2. Okay, so then this is great. We found a way to construct a Cayley graph of this form which has large chromatic number. For any k, we can get chromatic number k plus 2. So at this point, we kind of want to celebrate. We succeeded in what we wanted to do, only we also forgot what we were originally trying to do, which we want an odd distance graph of large chromatic number. And as far as I know, this is not an odd distance graph. So we need to take something slightly different. And for this, all we actually need to do to become an odd distance graph is to take a slightly strange primitive generating set. So now our primitive generating set is going to be this for t between 0 and 2k. We're taking elements in z squared of a form 2 to 2k plus t minus 2 to 2k minus t, the second coordinate, minus 2 to a t minus 2 to a 2k plus 1. So it's a stranger looking thing, but if you go through just Pythagoras, you can show that this is a subgraph of the odd distance graph on this lattice. And we still have the same lower bound for chromatic number, k plus 2. So the way to see that we should still have this lower bound is our key property of this generating set, the sandwiching property, that made us only fall into this bad case at most twice, was this power of 2 decreasing the first coordinate and increasing the second. And we have a similar thing going on here. The highest power of 2 dividing the first coordinate is decreasing as t increases, and the highest power of 2 dividing the second coordinate is increasing as t increases. So we have the same sandwiching property with our primitive generating set. So this thing still has large chromatic number, and so we get that the odd distance graph has unbound chromatic number. So one more nice thing I want to mention about this graph construction is that actually they also happen to be triangle free. You can somehow use the sandwiching property again to show that you don't have any triangles. So it'd be nice if somehow you could use this new technique of constructing triangle free graphs of large chromatic number to disprove any chi-boundless conjectures. But that's not something I've had any luck with yet. Okay. I want to go back a bit to this nice theorem we saw on coloring the integers. this was this nice classical theorem saying that if we have this polynomial with integer coefficients and constant coefficient 0, then in any finite color of the integers, we can find a monochromatic pair of distinct integers so that the difference is some value of this integer. So this fails, as we saw, if f of x is equal to 2x plus 1. So they needed something like this if of 0 equals 0 condition. But we saw going up to the plane, at least with this 2x plus 1 odd distances, things now work. You now have infinite chromatic number again. So there's a question of if you can do this for, if you can always drop this for a polynomial when you go up to a plane. And with Rose McCarthy and Michał Filipczuk, we're able to say that this is indeed the case. So if we have a polynomial of integer coefficients, then any finite coloring of a plane, we can find a monochromatic pair of distinct points so that their distance is some value of this polynomial. And we've just got this minor condition of taking the absolute value just to avoid some silly case of you could have some polynomial that's always negative. You could also just say the leading coefficient is positive, and this would be true. Okay. And another extension of this odd distance result we're able to prove, and this is one I really like a lot, is that it's also true for primes. So any finite coloring of a plane, you can find a monochromatic pair of points whose distance is a prime number. So I want to talk a tiny bit about how you can extend these methods to get these results. And I'll focus on this prime case. So before our primitive generating set was just going to be some odd integer distances. We don't want, and this worked nicely just because odd number times odd number is an odd number. But you don't have anything that nice for primes. So now we want our primitive set of generators to be unit distances. And then if you ever multiply this by a prime, it'll be a prime distance. So this is one difference, that our primitive set now needs to be unit distances. And now we're going to end up having to examine a similar kind of exponential sum. But now instead of having these odd numbers in the exponents times our alpha, we're going to have primes in this exponent times our alpha. And the exponential sum we end up needing to look at is of this form. We again have this averaging 1 over n factor. And this extra bit here, roughly speaking, is our linearly decreasing factor. Primes get more sparse as you increase. So that's what this log of our primes does. It counteracts that. So now things get more complicated. For alpha near 0, we want to do the same thing we want this to be positive, approximate by some integral, and that can work out of this weight function. But we end up getting a lot more bad cases than this alpha equal to 0, or alpha equal to a half. In the case that alpha equals to a half, this is going to be, again, just as bad with odd numbers, just because almost all primes are odd. So we fall into the same bad case there, with alpha being about equal to a half. But a similar thing can happen for any small number. So actually, if alpha is ever near anything, any rational with small denominator, then we're going to possibly be falling into one of these bad cases, just because of how points distribute. So we want to do a similar sandwiching trick, but now instead of doing it to bound away from this one bad case of a half, we're bounding away from the collection of bad cases of being near some rational small denominator. And then from some miracle from the results in analytic number theory, if we're bounded away from these small denominator rationals, then actually there exists results for estimating these exponential sums saying that this ends up being small, just like we needed before. So using these results from analytic number theory, where these exponential sums often come up, we can push through and get a good bound for our AC bound theorem for primes. Okay. One more result I'll mention is that you can also look at some analog of a Hedrickson-Nelson problem for pseudo-Euclidean spaces. So now, instead of just having some spatial dimensions, we also have some kind of temporal dimensions. And now when we look at a distance, in the spatial dimensions, we're going to be taking the sum of the square of the differences of the coordinates. And in the temporal dimensions, we're going to be taking the negative of the square of the difference of these coordinates. So this is how we get a distance in these pseudo-Euclidean spaces, ST. And then you can ask some analog of a Hedrickson-Nelson problem, what the chromatic number of unit distance graph of these things is. This was asked about 15 years ago. And then one other application of these methods is you can actually say that as long as you have at least two spatial dimensions and one time dimension, then again, the chromatic number of this unit distance graph is going to be infinite. And actually, you can do something a bit stronger. And instead of just looking at these points in R3, we can just look at these rationals cubed. So in any finite coloring of the rationals cubed, we can find a monochromatic pair, so that the square of the difference in the first coordinate plus square of the difference in the second minus in the third is equal to 1. Okay, so in the last few minutes, I'd like to just talk about some open problems. And one obvious open problem here is what happens if we only have one spatial dimension and more time dimensions. This is something I don't know about yet. Okay, so we now have quite a lot of distance sets, these odd polynomial primes, so that this distance graph on the plane will have infinite chromatic number. But we can ask about different kind of distance sets. And one that was asked a bit ago was what happens if we're just forbidding powers of 2 as distances. So is there a finite coloring of a plane so that there's no monochromatic pair of points whose distance is a power of 2 to the n? Our methods for trying to do something like this somewhat break down because, as far as I can gather, in order to get effective estimates for these kind of exponential sums, you really need your things and the exponents to not be growing too fast. As far as I can tell, if they're growing exponentially like 2 to the n, then you can't get these good estimates. So if you can solve this problem, I think there'll definitely be a lot to learn from that and can probably do a lot more. And another problem of a similar kind is if instead of looking at powers of 2, you look at factorials. So instead of finite coloring of a plane, avoiding monochromatic distances of the form n factorial. Okay. So I mentioned before that there was this nice spectral proof for measurable coloring that the odd distance graph has large chromatic number. But actually a more general result using another method was known quite a bit before this, which said that in any finite measurable coloring of a plane, we can find some large d0, so that for any distance greater than this d0, you can always find a monochromatic pair of points at this distance d from each other. So in particular, they said if we were forbidding some infinite set of distances going to infinity, then the measurable chromatic number will always be infinite. So optimistically, you might hope that something this strong could be true for non-measurable chromatic number. But actually, my belief is that this isn't the case for a non-measurable chromatic number. And there's a good conjectured counterexample to this. And this conjecture is that if you have a set D, which is algebraically independent, then you can actually find a finite coloring of a plane so that no monochromatic pair of points are distance d apart for some d in our algebraically independent set. So this is a conjecture I really believe, but it would have to be quite a crazy coloring. You know you can't do some measurable coloring, so it's not going to be any tiling. But I really do believe this would be true. Okay, stop there.
Okay, thanks, James. We could all unmute for a moment and give James a round of applause. On three, 1, 2, 3. So, do we have any questions?
Yeah, I can ask a question. So has anyone considered these types of problems with a different notion of distance?
Definitely for Hedgeridge-Nelson of unit distance they have. I don't know of any results for multiple distances.
For those examples that you gave at the beginning, the really bizarre ones that, I mean,
These
how
monster graphs.
yeah, how are they constructed?
So I know less about this unit distance one. This one for odd distance I looked at a bit. Actually, I can say one thing about the unit distance one, which is I know it contains a lot of these Moser spindles, these four chromatic things. I guess somehow maybe he was hoping to stick a bunch of these tightly together and you can get something higher. So roughly speaking, for this odd distance, he does a similar thing where he's bunching together a bunch of these larger 5 chromatic odd distance graphs. And actually, the way he does this, you can describe this graph in a simpler way if you're happy with it being infinite. His graph here ends up being a subgraph of some odd distance graph on a 4-dimensional lattice. Which it's infinite, but it's much easier to think about than this monster. So that was something that was encouraging for me to go back to this problem and try it again. But I don't have any interest in on how they build these things.
Okay, thank you.
I find de Grey's proof easier to think about if in the infinite dimensional case too, but
Okay.
eventually you have to do a computer check, which you don't do in infinite dimensions, but you've learned enough about the cut. You can take some lattices and color those and just say something about the colorings in those lattices. Then you say you put them together, and eventually you need to show something doesn't work, and then it would suffice to look at some finite subset for that.
Mm-hmm.
But so some parts of that proof I think are easier for the infinite case.
Yeah.
The Gray's proof's very readable, except for the fact that there's this computer check part. So one problem you didn't discuss here that I really like is this, what about just if I give you an infinite set of integers, and just say that's my distance set. I mean, that we don't know.
Yeah, I mean,
we don't know if it's possibly that it's always infinite, right?
Yeah, my guess would be that it's always infinite. If you have an infinite set of forbidden integers. I kind of feel like this algebraically independent thing is morally the only way to avoid it, but that's just a wild guess. And we seem a long way away from being able to do arbitrary infinite integers.
Oh. So you think, so if I give you an infinite set of algebraic numbers, and they're not all in some small range, that the chromatic number will be infinite?
Depending on what you mean by small range.
Like they shouldn't be like within some scale. Like they should be infinitely large, I guess.
Yeah.
So there should
But
be they should exist infinitely large things. They shouldn't be bounded. So if I give you so you believe that? That if I take
Oh yeah, I see. Yeah,
if I take an unbounded set of algebraic numbers,
My
that
guess would be yes.
the chromatic number's going to be infinite.
My guess would be yes, but that's maybe the most wild positive conjecture.
That'd be pretty nice.
Yeah.
I've got a question about so if you go back to one of the beginning slides,
Yep.
and you've got that pattern with the hexagons, which gives you a lower bound for of 5, right? Yeah.
This is for getting an upper bound.
Sorry, the upper bound of 7, yeah. So if it's in higher dimensions, well, firstly, do you also have an upper bound for when you've got, say, R3?
For a unit distance.
Yeah.
Yeah, so there's an exponential upper bound of roughly 3 to the d. And also a lower bound of something like 1.2 to the d.
So how does the construction for the this hexagon generalize if it does for the higher dimensions?
I don't know the details of that. It is some kind of clever tiling, but I don't know how they do it.
You can get a bound with not a clever tiling. If you take, I mean, if you just arbitrarily tile your space into little pieces, and then you make a graph where you connect pieces that have points that are unit apart, you're going to get, like, regardless of which dimension and however you choose your tiling, you're going to have bounded degree graphs. And then you can I mean, there is a coloring just because they've got bounded degree. There's going to be a bounded size coloring. So if I give you a graph with bounded degree, it's going to have a bounded chromatic number. So that same trick works in any dimension. You get the best bounds by cleverer tilings. And I don't recall what the tilings are, but it's not that obvious a tiling because I know that it improved like in the early 90s. One of the bounds improved, and so it wasn't the most obvious tiling if that's the case, because otherwise it would have already been known in the 60s, right? It was just an obvious tiling. That was it, and that was for 3 dimensions. But yeah, if you just take any tiling at all, if you sort of take any sort of just this like a grid tiling, just take the grid and you take cubes of radius less than diameter less than 1, and you just make this graph, it'll have bounded chromatic number.
So what is for R3, what are the best known bands?
It's between 6 and 15.
Okay.
I think it's 6.
Since you're saying 6, so in the plane, you think it's the lower bound? James?
What the answer in the plane?
Yeah. When you said you think it's 6, were you saying when you said you think it's 6, you think it's the lower bound is 6, or you think that? I thought you were saying.
Yeah, I was saying I thought the lower bound in R3 is 6. I think that's correct. If I was to take a guess in the plane, then I think 6 is the right answer. But again, this is another wild guess.
Yeah. Any other questions, James? If not, let's stop the recording there. Thanks, James.